Let me ask first, this is becoming my standard question. Are there any questions that you have dealing with the material that we discussed last time, material dealing with measures of central tendency and the issue of the range as a measure of variance?
How do you find the median again?
The median is the 50th percentile, so that you must either rank order scores from lowest to highest and then search for the middle score. Or you can transform that original stream of data into a frequency distribution and search for the middle score in that way. If the median is between two existing scores, for example, you have, as we did, 10 scores, and the fifth highest score is a score of 6, and the sixth highest score is, let's say, a score of 8. The median is equidistant between those two scores, so it would be 6 plus 8 divided by 2, which would be 7. Are there any other questions? Let's then today talk in detail about two other much more useful measures of variance or measures of variability. On the one hand, variance, and on the other, the notion of standard deviation. Let me first of all deal with the formula for the computation of variance. And I indicated to you that if we're talking about population variance, we talk about sigma, and if we're talking about sample variance, we talk about, or variance rather, sigma squared, and sample variance s squared. If we're talking about population standard deviation, we talk about sigma, and sample standard deviation, we talk about S. And there are implications when determining variance and standard deviation for whether you're talking about a population of scores or whether you're talking about a sample of scores. If you recall, when we talked about measures of central tendency, that was not the case. Regardless of whether we were dealing with a population or with a sample, we computed the mean in the same way. We added all the scores together and divided by the total number of scores. We computed mode in the same way. We computed median in the same way. That is not the case when dealing with measures of variability, at least when those measures of variability are on the one hand variance and on the other standard deviation. And we'll see that as we work our way through this. Let us simply look at initially the formula for the computation of variance. The formula for the computation of variance is sigma parentheses xi minus x bar parentheses squared divided by n. Let me just go through in a stepwise way what this formula says to you. It says, first of all, that you need 3 pieces of information. You need to know each of the individual x's, that is, each of the individual scores. You need to know the mean or average of those scores, and you need to know the total number of scores n. I have written here a stream of 10 scores let us presume 10 scores on a test of arithmetic. And the individual x's, the xi's, then are 4, 9, 9, 5, 2, 7, 6, 7, 3, 8. Given that information, we know two things about the data set that are relevant to the computation of variance. We know the xi's and we know n. What we don't know at the moment is x bar. So the first thing you have to do when computing variance is to compute x bar. What the formula then says to you is you subtract the mean x bar from each of the individual scores xi. That is, once we've computed the mean of this group of scores, we must subtract that mean from each of the individual scores themselves. What you will then have is a list of 10 different scores. Actually, the different scores are the differences between xi and x bar. The formula then tells you that the next step you must do is you must square those differences, generating a list of 10 squared difference scores. What you must then do is add those 10 squared difference scores together. You must sum them all together. And the last thing that the formula tells you to do is divide that score by n. And what results is the variance of the group. Are there any questions about what this formula tells you to do and in what sequence you're told to do those things?
Can you repeat step number 4 again?
Well, let me repeat the steps so that step number 4 has some context. Step 1 is to compute the mean of the scores. Step 2 is to subtract that mean from each of the individual scores. Step 3 is to square those 10 different scores. Step 4 is to add together those 10 squared difference scores. And step 5 is to divide that score by the number of scores, n. One of you at least has a question. Do we have to memorize this formula? And the answer is yes. There's an easier way to write it down or program it into your calculator. If you write it down, I will hunt you out and I will kill you. If you program it into your calculator, I will hunt you down and I will kill you. Jet Li has nothing on me. If you're fearful of having Jet Li come after you one day, I taught Jet Li all that he knows. You must memorize this formula. It's not a difficult thing to memorize. And what is more, I'm not asking you to memorize this score. This formula. I'm doing something stronger than ask. What would a word be? I'm requiring you to commit this formula to memory. It's not that the formula is just a vacuous piece of data. It's a piece of information that tells you, one, what variance is, and 2, how to go about computing it. We've dealt with the second issue, how to go about computing variance. But if you look at this formula, what is variance? If you were to be, it's Jeopardy, or whatever the music is to Jeopardy. You're on some quiz show, or you're at the pearly gates. Because a record of your grade in this course will be forwarded everywhere. You will one day get to the pearly gates, and St. Peter is likely to take out a text on data analysis and data collection. And I suspect that one of the first questions is going to be, define for me in 10 words or less the concept variance. Looking at that formula, what would you how would you define variance? What is it? Time stood still. Let me ask a different question. When you look at that formula, what does it tell you what variance is? Oh, I'm sorry, that's the same question. Let me phrase it another way then. When you look at that formula, what does it tell you what variance is?
So standard deviation squared divided by the sample size?
It tells you that because you know something of the relationship between variance and standard deviation, it tells you that variance is the standard deviation squared. I'm afraid St. Peter is going to say, wah, and you're going to find yourself on a slippery slope, rather like one of those tubes at the Schlitterbahn. Only you don't finish up in water. It's sort of like water, but it's very hot. So I'm told. Let me ask you this question. When you divide by n, anytime you divide by n, what are you doing? You're computing the average. You're computing an average anytime you divide by n. So first of all, we can say that variance is the average of something. Let us momentarily forget that we're dealing with squared scores here. What is this average the average of? Isn't it the average difference between each individual score and the center of the distribution? Except that that difference is expressed in squared units rather than in original units. So variance, although expressed in squared units, variance is the average difference between each individual score and the center of the distribution. So that as those individual scores become more similar to one another, and so more similar to the center of the distribution, variance will go down. As those individual scores become more dissimilar to one another, and so more dissimilar to the mean, the center of the distribution, that average variance will go up. So that groups of scores with high variance, data sets with high variance scores, are simply, you're being told that they're relatively heterogeneous. they're relatively dissimilar to one another. There are a lot of different kinds of scores in the set. When variance is low, you're being told that the group is relatively homogeneous, that the scores are relatively similar to one another. This is clearly not information provided you by the mean, the mode, or the median, and it's certainly not information provided you by the notion of range that we dealt with last time. Let's get rid of this lark. The first thing we then have to do is compute the mean of this set of 10 scores. Would you agree? We could do that by adding the scores together and then dividing by n, which is 10. Let's not do that. Let's compute the mean in a different way using a frequency distribution. Let's construct a frequency distribution. That is a distribution in which one column is a column of xi's and the other column is a frequency column, the frequency with which each of those scores occurs. Xi and f. And let's not bother including in this frequency distribution scores that are not in the original set. There is no zero score. Let's not bother putting it in there. The lowest score here is 2. There is also a 3 in the set. There is a 4. There is a 5. There is a 6. There is at least one 7. There is at least one 8. And there's at least one 9. Would you agree? Now all we have to do to complete the frequency distribution is to count the frequency with which each of these scores appears in this set. The score 2 appears once. The score 3 appears once. The score 4 appears once. 5 appears once. 6 appears once. 7 appears twice. 8 appears once. And 9 appears twice. Is that right? 2, 4, 5. So that there's a total of 10 scores. Just an observation as we pass through this. This distribution is bimodal. It has 2 modes, would you agree? There are 2 scores that occur more often than any of the other scores. 7 appears twice and 9 appears twice. So this distribution is a bimodal distribution. It has 2 modes. We now have to construct a column fx. That is, we have to multiply each individual score by the frequency with which it occurs. You understand that multiplying a score by the frequency with which it occurs is functionally precisely the same as adding those scores together. If there are 3 3s in a distribution, we can either go through the process of 3 plus 3 plus 3 equals 9, or we can multiply the individual score by the frequency with which it occurs. 3 times 3 is 9. So this multiplicative process is functionally the same as an additive process. 2 times 1 is 2. 3 times 1, 3. 4 times 1, 4. 5 times 1, 5. 6 times 1, 6. 7 times 2, 14. 8 times 1, 8. And 9 times 2 is 18. We now have to sum together that column. When we do this, do you understand that we're doing exactly the same functionally as adding together these 10 original scores? 2, 5, 9, 14, 20, 34, 42, 52, 60. So that X bar is 60 divided by 10, which is 6.0. Yes? Are there any questions at all about computing a mean from a frequency distribution?
Can you repeat the definition for variance one more time? You gave like an actual definition.
Can I repeat the definition for variance? Yes. You have another question? Will I? Of course, because I'm a good guy. Variance is the average difference between the individual scores in a set and the center of that set, the mean, except that that average is expressed in squared units rather than in original units. Are there any other questions?
Are we going to be dealing with the midpoints between the frequency and the...
Are we going to deal with class limits? No. No. Are there any other questions? So we know X bar. X bar is 6.0. We could treat this set of scores as a population, and we would know that mu equals 6.0. Do you agree? If this were a population of scores, then we would simply use the notation mu rather than X bar, but the mean would remain the same. Let's get rid of fx. This is such power. I don't like fx. I never did. So I got rid of it. We now have all three pieces of information that we need to compute variance. We know the individual scores, we know the mean of the scores, and we know the number of scores. So let's proceed through the computation of variance, but do it from using a frequency distribution. Having computed the mean, the next step, would you agree, was to subtract the mean from each of the individual scores. So let's do that. Let's have fun. Let's subtract the mean from each of the individual scores. xi minus x bar. Well, that's not good. 2 minus 6 is minus 4. 3 minus 6 is minus 3. 4 minus 6 is minus 2. 5 minus 6 is minus 1. 6 minus 6 is 0. 7 minus 6 is plus 1. 8 minus 6 is plus 2. And 9 minus 6 is plus 3. Are we all still riding the horse? We're all still riding the horse. The next step in the computation of variance, well, let me make a note as we pass by. Do you realize, do you understand that using a frequency distribution, we have not computed all of the xi minus x bars? Because there are 2 3s and there are 2 1s. Because 7 appears twice and 9 appears twice. And so far, We haven't been sensitive to that. Having said that, let's go on and have even more fun by squaring these different scores. That is xi minus x bar squared. Minus 4 squared is 108, or it might be 16. Minus 3 squared is 9. Minus 2 squared is 4. Minus 1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. Are we all still on the horse? At some point here, we have to recognize that there is not a single 7, there are 2 of them. And so there is not a single 1, there is 2 of them. And so there's not a single 1 in the squared difference column, there are 2 of them. Likewise, somewhere along the line, we have to recognize that there is not 1 9 but 2. So there is not 1 3 but 2, and there are 2 9s as well. So why don't we do that now? Why don't we multiply each of these squared difference scores by the frequency with which they occur? 16 occurs once because 2 occurs once. Similarly, 9 occurs once. 4 occurs once. 1, 0. But there are 2 7s, so 1 becomes 2 times 1, which is 2. There is a single 8, 4. There are 2 9s, so there are 2 3s, so there are 2 3 squareds, 18. Are there any questions? We now have to sum together this column. When we sum together this column, what we're doing is generating the sum of xi minus x bar squared. Oh, let me get that right. So we add this column of scores together. 16, 20, 29, 30, 32, 36, 46, 54. Is that right? Yeah? So that the sum of xi minus x bar squared is 54. You now have the numerator for the computation of variance. In order to compute the variance, you divide by n. You divide by 10. So that the variance is 5.4. Are there any questions regarding how you compute variance? More specifically, how you compute variance if you're given a frequency distribution, which you will be given on the exam. And you will be asked to compute the variance. Actually, you'll be given a frequency distribution. I feel like spilling the beans. There are no secrets about this. On the exam, you will be given a frequency distribution, and you'll be required to compute the mean, the mode, the median, variance, standard deviation, and range. Are there any questions regarding how you compute standard deviation using a frequency distribution? It seems to me that the only wrinkle computationally is that at some point you have to be sensitive to how frequently the individual scores occurred, and so how many of these squared difference scores there are. Yes.
Could you go over one more time after we get the square root to go on to the rest of it? Just that one last column?
After you get the square root, we haven't got the square root of anything yet. After you've, okay. I think I'm with you. We'll go back. Don't worry about it. Don't worry about it. Better to ask now than be sitting there with the exam in front of you going, God, I wish I had asked. Yeah? And believe me, if you are unclear on it, somebody else in here is. And so will future generations. Isn't this just amazing? First of all, you have to subtract the mean from each of the individual scores. And we've done that in this column. The formula for variance says you then square those different scores. And that's what we've done in this column. The problem is that we have not dealt with this original set of scores, at least not as 10 individual scores. We could have done. We could have subtracted 6 from 4, from 9, from 9, from 5, and so on. But we didn't do that. We chose to be more sophisticated. We chose to be like the French. A very positive statement about the French. We chose to construct a frequency distribution, or as they say in France, the frequency distribution. I crack myself up anyway. That has implications for two of the different scores here. For this different score and for this different score. Because they're based on original scores from this set that don't appear once, they appear more than once. In fact, the score 7, and so this squared difference score 1, appears twice. How do you get over this problem? You simply multiply the squared difference score by the frequency with which it occurs. So 2 times 1 is 2. Likewise, this squared difference score 9 is based on a score that appears not once but twice. How do you overcome that problem? You multiply the squared difference score by the frequency with which it occurs. 2 times 9 is 18. Now you have a set of data that would correspond absolutely to the set that you would generate had you started off by subtracting the mean from each of these 10 scores separately and progressing in that way. So now, when you're up with St. Peter, and you've answered the question about the conceptual definition of variance, and St. Peter has gone, all right, you must have taken that course with Douglas. Now St. Peter says, I've got some numbers for you, and I've actually arranged them in a frequency distribution because I'm French. Compute the variance of those scores. You would feel comfortable that you could do that. Because if you don't feel comfortable you could do that, you have questions. Yes?
Are you going to give us examples to
Am I going to give you examples to do? I might. Now, if I speak to future generations, yes, you will get examples. They will appear as assignments on the Vista page. Yes, I'll give you some. I'll give you a data set and require that you compute measures of central tendency and measures of variability. Yeah. Are there any other questions?
All right, so after we compute the variance, how do we know if it's considered high or low variance?
You don't.
Okay.
And so you say, well, why compute the variance then? You didn't ask that question about the mean. And you could have done. So we compute the mean and it's 6. What is that? Is that a big number or a small number? I'm answering your question. The usefulness of a mean score is when you can compare it with another mean score. So that you can say this group this group scored 6 on the test on average, and this group scored 8 on the test on average. It's even more magic if you did something to the second group that you didn't do to the first group. You used a different teaching method or a different textbook. Now you can compare the two, and you might reach the conclusion that the second teaching method or the second textbook is superior to the first. Likewise, variance scores are most useful in a comparative way. And then you can say this group of scores is more or less homogeneous than this group of scores. And it's not inherent in the number. Had we used bigger numbers, had the test been a 100-item test, we would have had a higher mean and a higher variance. Well, we would certainly have had a higher mean. So the meaning of these measures is not somehow inherent in their value. Are there any other questions? Yes.
You have to judge whether or not the variance is high or low based on the range of the score.
No. Let's slide right by this issue, because you can only say that the variance of one group is higher or lower than the variance of another group. You will not be asked, because you cannot answer the question, if the variance of a group of 10 scores is 5.4, is that a lot of variance or is that a small amount of variance? You can't answer that question, and you won't be asked that question on an exam. How do we go about computing the standard deviation of this set of scores? We simply take the standard deviation is simply the square root of the variance. So the variance of the scores is 5.4, and the standard deviation of this set of scores is the square root of 5.4. We're still all running together. It's like the Tour de France. Are we still in one group? Do we have just one peloton? Nobody's been left behind. That shh, as the pedals and the wheels turn, we're all together. Yeah. Riding through the French countryside. There's a problem. And quite honestly, I don't know how to solve it. So I'm just going to make up a solution. When you compute population variance, you do it in the way, and population standard deviation, you do it in the way, follow the process that we just followed. That is not the case when you are computing sample variance or sample standard deviations. And that's all I know. I wasn't there for the lecture, you know, when they talked about sample standard deviations and sample variance. But I think that you get around that by using not n as the denominator, but n minus 1. So if we're computing sample variance, that is s squared, the denominator is not n, it's n minus 1. So that the variance of this set of scores, if this set of scores were a sample, is 54 divided by 9. Yeah. Which, if memory serves me correctly, is 6.0. So whereas sigma squared was 5.4 and sigma was the square root of 5.4, s squared sample variance is 6 and s sample standard deviation is the square root of 6.
Why is it 54?
We just went through, didn't we, computation of... We went, the first example of the computation of variance used n as the denominator. What that signifies is that you are treating the group of scores as a population. So that the variance was 5.4 and the standard deviation was the square root of 5.4. If the group of scores is not a population but a sample, which it most usually is, you divide not by n but by n minus 1. So if we were to treat this set of scores not as a population but as a sample, the variance would be 54 divided by n minus 1, which is 9, so that the variance would be 6 and the standard deviation would be the square root of 6. Are there any questions?
Why did we add the frequency? Like when we were adding and we got 10, why did we decide to add that?
Why did we decide to add what?
The frequency, like how we added 1 and 1 and 1 and 1 and 2 and 2. Why did I don't understand why we did it, or how we added and we got 10 at the end of the column. Why did we do it?
I simply indicated if we count the number of individual scores in the original set, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes? When you generate the frequency column, that is the frequency with which each individual score occurs, you can check to ensure that you've included all of the scores by simply adding that frequency column the scores in that frequency column together. And when you add the scores in the frequency column together, you again arrive at 10, suggesting that we included all of the original scores. Are there any other questions dealing with variance or standard deviation? Unlike measures of central tendency, which seek to express in a single score something to do with the center of the distribution, measures of variability seek to express in a single score something to do with the relative similarity, dissimilarity of the scores in the distribution. So that the higher the variance score, the higher the standard deviation score, the more dissimilar the original scores are to one another, and the more dissimilar they are to the mean. The lower the variance score, the more similar the scores are to one another, and the more similar they are to the mean. Are there any other questions? Let me ask you a question. Why would we prefer, as a measure of variability, why would we prefer variance and standard deviation over the range?
The range just covers two numbers, like the highest and lowest, as it's more sensitive to, well, the standard deviation, right, is more sensitive to the, as a whole, the, I don't know.
Yeah, I mentioned this at the end of the last lecture, why the range statistic was essentially useless. It's essentially useless because it's sensitive to only two scores, the highest score and the lowest score. No matter how the other scores change, the range remains the same, to the extent that the highest score and the lowest score remain the same. Clearly, variance and so standard deviation are sensitive to all of the original scores, so that compared to the range statistic, variance and standard deviation retain more of the original information. And the criterion at the outset here, when we started dealing with measures of central tendency and measures of variability, was you make your selection which to use based on which of them retains most of the original information. And when you're discussing measures of variability, it's obviously the case that both variance and standard deviation, because they're sensitive to all of the scores in the distribution, retain more of the original information than does the range statistic. We're all just riding along together. I hope we're all riding along together, because this is straightforward stuff. This is straightforward stuff. We haven't got into the mountains yet. Yes.
You said that variance is high when it's further away from the mean, right? And low when it's closer to the mean?
Variance increases as the original scores become more heterogeneous. That is, they become more dissimilar to one another, and therefore more dissimilar to the mean. Variance goes down as the original scores become more homogeneous, more similar to one another, and so more similar to the mean. Let's just take an example, very simple example. Two groups, Group A and Group B. They both have a mean, would you agree, of 4? Yes? They both have a mean of 4. 8 plus 4 is plus 0 is 12, divided by 3 is 4. 4 plus 4 plus 4 is 12, divided by 3 is 4. But clearly, these groups are dissimilar internally. If you were to compute the variance of Group B, what would it be? The variance of this group of scores would be 0. Because you subtract the mean 4 from each of the individual scores. 4 minus 4 is 0, 4 minus 4 is 0, 4 minus 4 is 0. You've got difference scores all equal to 0, so all of your squared difference scores will be equal to 0, so the numerator will be equal to 0. When you compute the variance for this set of scores, will it A, be less than 0, B, be equal to 0, or C, be greater than 0? It will be greater than 0. Because 0 minus 4 is minus 4, 4 minus 4 is 0, 8 minus 4 is 4. You've got two different scores of 4. You square those, 16. You sum those together, 32. And you divide by the number of scores, 3. You got 10.67. The variance of this set of scores, if treated as a population, is 10.67. As variance goes down, it indicates that the scores in the group are more similar to one another and more similar to the mean. As variance goes up, it indicates that the scores are relatively dissimilar to one another and so relatively dissimilar to the mean. Some things in this course will have a relatively short half-life. The issue of levels of data, nominal, ordinal, and interval and ratio, has a relatively short half-life because very quickly we'll discover that we're dealing with interval and ratio data and that will be the end of it. Some of the issues in this class don't go away until the semester ends. And two things that do not go away are, on the one hand, the mean, and on the other, variance and standard deviation. Because essentially all data analytic techniques that involve the comparison of one group with at least one other group are based upon knowledge of the mean scores of those groups and the variance or standard deviations of those groups. And I say that to emphasize the significance of the issues that we've covered. That's not to say that you should not, for the purposes of the first exam, understand what the range score is and be able to compute it. It simply indicates that the shelf life of that particular concept is limited. We're not going to talk about it after the first exam. And we probably won't talk about it between now and the first exam. I have distributed, or the next meeting will deal with the issue of measurement reliability, which is explained in Supplement 1. If any of you do not have a copy of that, please pick one up. Otherwise, I will see you next Tuesday.